for people. Okay, so let's start the past seminar series. Welcome everybody. I see a lot of researchers and students who have joined us, in person and on Zoom. So I am delighted to introduce Professor Ehsan Hashemi, who comes to us from Edmonton, Canada, from the University of Alberta. And as you can see on the screen here, he's a professor in the Department of Mechanical Engineering. He runs the Node Lab, and Professor Hashemi is a super interesting person. He, originally from Iran, got his PhD in Waterloo. He's been a visiting researcher in Germany and Sweden. Then came back to Canada, and now he's at the University of Alberta. Another really important thing, and how I got to know Professor Hashemi is he was the chair of the 2024 International Conference on Intelligent Transportation Systems. Did an amazing job running that conference that everybody enjoyed very much, and got to know him a little bit and learn a little bit about his work. And I asked if he'd be willing to come and share more with us, and he was super kind to say yes. I will mention that so 4:15 local time, he's got to get out and go teach his class. So of an abbreviated seminar. So we got to be done at that point with the presentation and questions. But I won't take any more time. Thank you so much, Ehsan, for joining us.
Thank you so much, Scott. Thanks for the nice introduction, and nice to meet you all online and in person. It's my pleasure to have this talk in your group and the PATH group. And I'm going to talk about some of our recent progress on the distributed estimation and distributed motion planning with application on intelligent transportation systems and intelligent mobility. And again, thanks for having me in this session. I would be happy to answer any question at the end of the presentation. And for sure, if you are interested to know more about our research, you are welcome to see our webpage. And if you have any questions, just let us know. All right.
Encourage folks chat if they wish.
Yeah, thank you. All right. As Scott mentioned, I'm an associate professor in the Department of Mechanical Engineering at the University of Alberta, Edmonton, Canada. And I'm the director of the Node Lab, Network Optimization, Diagnosis, and Estimation. Our research project or programs are mostly focused on the network control systems, perception-based motion planning, distributed estimation for connected automated driving systems, and safe human autonomy interaction. This is a picture from University of Alberta, as you can see, and at the center is one of the buildings that my lab is located there. This is just, I usually at the beginning of a presentation introduce my group, because the whole thing that has been done, or I'm going to present, is the collective efforts by these amazing students and researchers, not my job. They have done the main job. I just supervise them. So I have different postdocs, PhD, master students, and undergraduate research assistants that they have been doing an amazing job in terms of enhancing safety and reliability of intelligent mobility. And some of them are visitors from Europe. Some of them are my students here, but we have a very nice group here working together with focus on intelligent mobility systems. My research talk is focused on the research on two main research themes that we do under the distributed systems. The first theme is the distributed estimation and perception. And for that, our main application is both network robotics and automated driving systems. On the left side, you can see the network robot that we have, different drones and the mobile robots in terms of heterogeneous network control systems. And we do the state estimation using this network of robots through different multimodality in the sensing systems, including the LiDARs, cameras, and the inertial measurement units to estimate their states, and then also share the information, share the perception with the other robots in the environment. And for with focus on the intelligent transportation systems, we have, again, the distributed estimation projects with the main aim of enhancing the safety of the roads for the occluded scenes and also for the cases that we have safety critical scenarios, for example, for the pedestrian jumping in the road or the scenes that are perceptually degraded or suffering from perceptually degraded conditions. On the right side, you can see our perception vehicle. It's not an autonomous driving vehicle due to several safety reasons, and we also are trying to get the approval from the Ministry of Transportation to be able to drive this vehicle on the road. But right now, we just use this vehicle as a perception vehicle, and it has also the 5G enabled connection with communication with the infrastructure sensors or base stations, and we also have the high fidelity simulators for the remote takeover, remote assistance to these automated driving systems. Our main approaches or the theoretical work that we do throughout this project, the distributed estimation and diagnosis, is under the umbrella or under the framework of the event-triggered algorithm for distributed optimization. And the reason is we are not able to have the constant communication between the autonomous mobile robots or automated driving systems and the base station due to the power usage, due to the packet drop, and also the communication delay. We prefer to not only it's not a matter of preference, it's just a matter of feasibility and the dynamic scenes. And with the physical constraints that we have, we are developing event-triggered systems, which means to develop stable control systems with asymptotic stability, to be able to communicate with the other agents or mobile agents in the scene, but using an event trigger based on the safety critical situations or based on the specific thresholds or the criteria that would meet in the environment. Then we're going to trigger the communication, and then this system would evolve throughout that communication for a short time. I just want to provide some specific examples that we have been successful in delivering the outcomes also to our industry partners and with the technology transfer. On the left side, you can see in the picture on the left side, you can see a mobile robot that is moving on the highly slippery surfaces. And as you know, when it comes to the larger slip, the odometry solution is not valid anymore. And we need to use the onboard sensory measurements, specifically proprioceptive observers, to design a state estimator that would be able to estimate the state of the system subject to sleep and subject to perceptually degraded conditions. The classical solutions for that are visual inertial navigation systems, bundle adjustment problems, loop closure systems, but all of them are, again, under the unique optimization problem or the generic optimization problem that we try to minimize the state estimation error using this multimodality in the system and subject to some specific constraints, assuming we have bounded uncertainties in the model. For sure, if the uncertainty in the model goes above a specific thresholds, the validity of the model is under the question, and we need to do some modifications. But these are all under the assumption of bounded uncertainties for the model. In terms of payload for these robots, we are talking about ranging from 5 kilogram to 15, 17 kilogram. With these payload variation, we would still be able to deliver the invariant observer design for these slippery conditions. On the right side, you can see the one of our vehicle on the industry partner test platform that we have, and the vehicle is located on different surfaces, dry surface and the slippery surfaces. And as you may know, the main challenge with the vehicle stability control systems are nonlinearities in the tire forces, specifically combined slip tire forces. That longitudinal slip will also affect the lateral force capacity of the tires in highly slippery surfaces. This brings up a huge challenge for the state estimation due to the value of slip, and also brings up a huge challenge in terms of motion planning. When we have the limited tire capacity, motion planning for adverse weather condition that we are suffering from that a lot in Edmonton and specifically in Alberta is under a big question. So one of our main objective is designing a reliable state estimation, then designing a reliable motion planning for vehicles under the larger slip conditions or the mobile robot on different surface conditions. The whole idea here for the state estimation is, or the contribution here is using the information from all corners of the vehicle, from all tires. And we treat this as four different nodes or four different agents that they provide the odometry, they provide the initial information, initial measurement unit information, and they will all gather into a complete graph. And then with the trace minimization of the Laplacian of this graph, we would be able to minimize the state estimation error throughout the linear consensus algorithm that we technically reform or recast this problem onto the consensus problem for each agent or each corner or each node of this vehicle, which are technically the tires or the corner modules for this vehicle. And then by this recasting, we would be able to say, okay, this is the reliability of the one corner or the tire. This is the reliability of the other corner or the tire. How we can deal with this to enhance the whole reliability of the state estimation of the whole structure or the whole system. After we estimate these states, we also need to control that. But the thing is, when we have a platoon of the vehicle, or when we have a connected vehicle structure in the highway driving or urban driving scenarios, when we have emergency situations that could be immediate accident in the road or immediate appearance of pedestrian in the road, it might be very late for the vehicle behind the line, or I mean behind the platoon or the last location of the platoon, to do the braking or proper maneuvering or proper steering to avoid that. With the distributed estimation and distributed control strategy that we propose in this research, we were able to have more proactive action in terms of braking or steering of the rear vehicles in the platoon. As you can see here on the right side, the gray lines show the activation of the ABS with those several pulse modulation to minimize the slip ratio, to enhance the safety of the vehicle for proper brake distance. But as we can see, with this linear consensus assumption and designing a robust control for each vehicle within this path with the distributed estimation structure that I mentioned in the previous slide, we were able to minimize the slip ratio on each tire, as you can see with the black lines and all of these plots, and then enhance the safety. And as you can confirm, there is no even ABS activation using this distributed control structure. Why? The reason is the vehicles behind the platoon were informed more proactively and in a timely manner. And then everything is under the robust control strategy, how to design a distributed robust control within this whole framework. We also extend this to some indoor applications for network mobile robots. We have a network of mobile robots working in the indoor environment with different applications on the warehouse robotics or the healthcare robotic systems. And we have stationary sensors and onboard sensor measurements. What we do is, again, we use the multimodality on the sensors, for example, the visual part and the LiDAR part, and we would be able to estimate the position of the robots and then communicate that with the robot just in case there is an occlusion in the scene. The advantage of the stationary sensor systems is they're not suffering from the highly dynamic scene, because using onboard sensor measurement, when we try to estimate the position of the robot, when the whole environment is very dynamic, obtaining the proper visual odometry solution is very challenging. Why? Because all of the features are moving, and it's hard to establish or construct the odometry around those moving objects unless we know our motion of the robot very meticulously. So the communication between these stationary sensor units and the robot was very effective for different applications, for different warehouse applications project that we had. And as you can see on the bottom right, figure 2, we were able to even to detect the robot using the point cloud and these infrastructure sensor nodes, even with the minimized region for the detection. And we have several publications on this. If you're interested, you can take a look on these publications or contact me to send you the whole methodology. But here in terms of theoretical contribution, we had two contributions. First of all, bring this problem into some multimodal data fusion structures, including the covariance intersection, distributed estimation using linear consensus, and also robust observer design and invariant observer designs. Why? Because of the different or heterogeneity in the noise levels that we have from different sensors, and also different field of view. The second research theme that I want to talk about that today is, and also our progress on that, is autonomous navigation and distributed control. How we are able to enhance the reliability of the motion planning in a distributed structure, in a distributed architecture, when we have different agents, specifically intelligent mobility applications. For that, we were able to, one of my PhD students was working on the prediction, path prediction or trajectory prediction for pedestrians. And the other one was working on the distributed control of automated driving system, having this path prediction information. For the trajectory prediction of the pedestrians, we were able to detect or predict the trajectory up to 650, 700 milliseconds. And in the urban settings, still this number is very valuable in terms of enhancing the safety. And what we do is we form potential fields and the barrier functions around the humans, and by including some social aspects into that, and then having a prediction from the viewpoint of the automated driving system using camera and using LiDAR to have a forecast on the position of the pedestrians in the next 700 milliseconds. And in the larger framework, we were able to put this prediction into the distributed control architecture to have a better motion planning. And the motion planning, the contribution of our team in the more distributed motion planning is again bringing the slip conditions into the whole picture, which means how the slip will affect the whole dynamics of the system and also will affect the reliability or the physical constraints of the system. And then we put that into the distributed motion planning architecture. In terms of safety of the one or enhancing the safety of the automated driving system, we were also able to recast this problem into the game theory to enhance the reliability and safety. And the whole idea is if we have different control actuation at each corner, how we would be able to enhance the reliability of this controller if each of these actuators are working independently because they're coming from different vendors. The traction control system may come from another vendor, but the stability control system of the vehicle may come from another vendor for the OEM applications. And we were able to recast this problem in the non-cooperative game that each of the players are different control actuation systems. And it was also tested in high fidelity simulations and also the partial and the real experiments on the vehicle that we had. And it enhanced the safety significantly, specifically on the slippery surface conditions. And right now we are in the process of scaling this up to the multi-agent systems or multi-vehicle architecture. Another part of our research is dedicated to the LiDAR and the data fusion using the LiDAR information. And the application is specifically for the SLAM solution, specifically for the SLAM solutions in the large dynamic environments. Again, the same idea using the linear consensus, but using the multimodality in this framework. Using that multimodality, using LiDAR and the visual part, we were able to not only have the state estimation over the vehicle, but also having mapping in the environment. And again, the publications are there. If you're interested, just let me know and we would be able to share this. And one of the recent contribution is reforming this LiDAR perception into the motion planning and having a direct mapping of the LiDAR point cloud into the cost map, and then do the motion planning effectively for the highly dynamic environments, specifically around the campus that we have several uncertainties due to the public transportation and the public vehicles. And the last part of our research that I want to discuss about that right now is again connecting to the infrastructure sensor nodes and how we enhance the safety of this. The whole idea is again using a linear and nonlinear consensus to use the information from the stationary sensors and fuse that with the onboard sensor measurements to enhance the perception, field of view, and also the estimated states. In terms of the force estimation, we were able to estimate the tire forces in different road surface friction conditions and with different actuation systems. We are ranging our state estimator is able to do the estimation ranging from the electric vehicles to the open differentials and also electronic limitless slip differentials. And we tested them on different scenarios, including high drift or highly slippery surfaces. These forces are used in the motion planning and control architecture that I discussed just quickly. And these are the two main research themes that I wanted to talk about this. For sure, there are lots of collaboration opportunities as well as the interesting talks to continue this research with the PATH group, and it's more focused on the distributed optimization that my team definitely can contribute to, and also remote assistant and takeover for automated driving systems. And in terms of practicality, we would be able to definitely contribute to the multimodal state estimation. That was all regarding my research that I wanted to share with you guys. And these are some of our research funding institutions and also the collaborators in Europe and also States and in Canada. Let me know if you have any questions.
All right, amazing. Thank you so much. Wow, that was like 20 minutes. So a good time for some questions, and then maybe we'll even get out early. So if you
Sorry, Scott, is it possible that I join again in 1 minute from now? I just need to change my room. Is it possible to just rejoin in 1 minute?
no problem, we'll be here.
In 1 minute, yeah. I'll rejoin.
For those that are here, you can queue up a question in the chat if you have it, and I'll bring it up. And of course, those in the room can feel welcome to ask as well.
Sorry, Scott and the team. I joined
Yep,
again.
that's great.
Sorry, they took they took the conference room for a new event, but that's fine. I'm here.
Great, great. And you can hear us.
Yes, yes.
Okay, excellent. So I'll maybe start the questions. First, something that is very interesting to me is that, basically the two themes you have in much of your research is, you've got some distributed sensing that you can do things that you can estimate the environment to assist with automation of vehicle systems, and there's kind of many applications of that concepts. I wanted to ask you about theme one, and something that strikes me too is that in Alberta you've got weather and slippery roads. You talked about robotic applications, and they can be on surfaces that are not that don't have grip. But if you could show the slide on theme one, where you described, I think, using vehicles to individually gather data and then do some consensus-based algorithm to estimate slip. I'm wondering if you could bring up that slide in theme one. And my question is, yeah, next one, I think on slide 8 is the one I'm interested in. Yeah, here.
Yes.
Well, I guess this is how it could apply, but um, uh, maybe you mentioned it, but it went by quickly on slide 7. But what are the signals that are sent from the vehicles
Yes.
into the infrastructure to perform the consensus-based estimation?
Yeah, very good question, Scott. I would like to clarify that these slide number 7 and slide number 8 are completely different. I mean, the same idea, but they're completely different in terms of the architecture. Slide number 7, and this research right now is for state estimation locally using onboard sensor measurements. There's no communication between the vehicle or between the robot and the infrastructure. Here, the idea is recasting the problem of the state estimation with different actuators to a problem of the distributed estimation using different agents at the corner of the vehicle. And the range of sensors that we are using here are mostly proprioceptive sensors. I mean, for the vehicle, we use the IMU sensors and also the wheel encoders. We use that in the first stage. The second stage that right now we are doing so, we are also fusing the visual part into the picture and the
Mm-hmm.
light. You definitely know that for the visual part is not reliable for the dynamic scenes because we cannot establish the visual odometry on that. So here we should mostly rely on the IMU and the wheel encoders to estimate the slip and also the state of the vehicle. But the next one here, we use connectivity between different vehicles and also between the vehicle and the infrastructure to enhance the perception, number one, and also do the control, number two. What sensors we are using here? We use the camera, LiDAR, and the IMU, onboard IMU. And the idea here is just use the infrastructure sensors or the stationary sensors to address the cases that the front or the rear vehicle is suffering from the occluded scene. There might be a pedestrian jumping in front of a double decker into the street, and the rear vehicle have no idea about that. This base station or infrastructure sensor nodes would be able to communicate this with the vehicles in the vicinity. Not constant communication, but in terms of the safety critical situations, they see the imminent danger and they can communicate this with all vehicles in the vicinity that at this distance, or because we also have the HD map information in the scene. At this distance, at this location, there is a dynamic object, let's say pedestrians or the scooter or the vehicle, and this light message could be sent directly to all vehicles in the vicinity.
Okay, got it. Yeah, with it going by quickly, I did mix some things, and now I understand that you got sensors on board the vehicle, but then infrastructure provides more sensory signals, you know, uh, like understanding a VRU that's further up the road.
Yes, yes. And the same idea also was tested for indoor applications, that the infrastructure sensors or stationary sensors, that here was only RGBD camera. In one case, the other case was fisheye camera. Even it doesn't provide the depth information. The team was able to estimate these positions and the states, especially for the occluded scene, that the human is in front of the robot, and it happens a lot. It's technically the project that we had with one of our industry partners, that the humans that are working in the warehouse robotics many times occlude the scene, and they're pretty dynamic. So the onboard sensory measurements from the robot is not sufficient to detect those or to cover the better area. But with this idea of the distributed estimation, distributed perception, at least we're going to have a better understanding on the cost map to generate than having a proper motion planning.
Mm-hmm. Mm-hmm. Got it. Cool. Any others with questions?
And I also would like to add one thing. For sure, I can answer the questions after this, but right now we are testing in the final slides I mentioned about the LiDAR. For example, here we are moving towards computationally efficient visual LiDAR frameworks to enhance the accuracy of our perception. For the local motion planning architectures, both for automated driving systems or for fast mobile robots, the dynamic scene and also the different lighting conditions is very challenging for the visual-based perceptions. On the other hand, the snowflakes and the reflection from the snowflakes on the LiDAR is a big challenge for the pure LiDAR-based estimation. Right now in the team, we are working on this multimodality. And also, in addition to that, we have radars to generate this cost map in real time. By real time, I mean between 50 to 60 milliseconds. We were not able so far to reduce this time as a sample time. But between 50 to 60 milliseconds, we are able to do the perception and generate the cost map around the vehicle. And this is an ongoing project with one of our industry partners. And as one of the products or derivatives of this, we are also able to have an accurate state estimation on the other dynamic objects in the scene. Estimating the heading angle
Thank you.
and the velocity of the other vehicles in the dynamic scene is pretty challenging when it comes to the urban settings. Because of even a little bit of heading angle from 0 to 5 degrees, it's not detectable using normal filter-based method or normal linear, nonlinear observation or optimization-based methods. We are using highly accurate radars and LiDARs to enhance that heading angle estimation, specifically for this project as well.
Mm-hmm. Yeah, the perception and the prediction of their pathway is quite a difficult problem. That reminds me of another piece. You mentioned this, game theoretic formulation of different control systems conflicting with each other.
Yes.
So, I think some OEMs have had trouble, again, related to perception in say with detecting objects ahead, camera might detect an object, but then radar might not detect the object or vice versa. And then, fusing these or trying to um, find some resolution to this conflict has become an issue. So, for example, famously, Tesla got rid of their radar. They just said, forget about it. Um, what do you think about this problem and how to deal with it? I mean, what you described here, I think, is an instance where you have a that has all these suppliers and they don't integrate well.
Yeah,
So, what do you think of that problem?
very good question, Scott. We are still working on the controller side. As you can see in this slide, the the challenge for the controller could be addressed a little bit more easier because it could be recast into a game, a classical game structure, which means we might have cooperative or non-cooperative game with different players. We know the control. We optimally generate the control actuation to reach to a specific cost function or minimize a specific cost function. But for the state estimation, we have the same issue here right now.
Mm-hmm.
The radar and the LiDAR have different detection performance and the detection reliability. But when it comes to the voting, when it comes to the consensus, which source of information you can rely more on? And the whole problem will be funneled down or will be reduced to the reliability measure estimation. If you know that this is the variance, not specifically the variance, the reliability of the visual part throughout the online data analytics, then you would be able to more rely on the visual part for the detection or more rely on the semantics for the detection rather than the radar. So the challenge that we have right now is the online or real-time data analytics to obtain that reliability measure right now. But we do not have the specific answer for that these days. This is the project that we are working on.
Yeah, this is an interesting question. Okay, we have a couple more minutes, of course. Any other questions?
I guess, oh, I can hear my voice.
Should I speak through here?
No, you can speak as
Okay,
as
so-
you are right now. The owl will pick it up. No need to.
Hi, Dr. Hashemi. Thank you so much for your presentation.
You mentioned like B2X, UI infrastructure technologies. I'm
Hey,
curious.
Linda, speak up because I muted your laptop and it'll
okay.
pick you up in the owl.
Okay. So what do you think the challenges are, like, to getting some of these companies to integrate like V2X capabilities more? Because every company's doing it differently. Tesla, as Dr. Moore mentioned, is just doing camera as well. Waymo's doing LiDAR, radar, and camera. But I think that the missing component is that V2X and V2I technology. But then the challenge is like real-time data, having that acquired. So I guess I'm curious, like, what are some of the challenges of these companies? Like, why is it that we haven't really gotten to that point yet where we've integrated that? We've already gotten like LiDAR and radar technologies into these autonomous vehicle systems, but I haven't really seen any company have already utilized truly V2X and V2I capabilities.
Can I add on that? I'm also curious if in Canada, the Ministry of Transportation has some different thinking about connected and automated vehicles or regulations or requirements of these types of technologies.
Yeah.
If you could give us like the non-United States perspective, that'd be
Yes.
pretty.
Yeah, very good question, Linda and Scott. Again, I wanted to provide this answer that I think policy, not 100% sure, at least as far as I saw for the last 3 or 4 years, the policy for the communication, specifically for the V2X communication, is opening up way faster in Canada compared to US, as far as I saw and as far as I checked. And Linda, the key point previously, or the major comments that they had, was specifically for the safety or security of the communication in terms of cyber attacks, and also in terms of the specific packet drops or safety critical packet drops. But right now, with the huge advancement in the communication technologies, and also the reliable constant communication systems with low power, this has been addressed very effectively. So I predict the main advancement in the recent decade, I mean for the next decade, would be bringing into V2X, V2V, V2I communication into the picture way more effectively, because there is a limitation for onboard sensor measurements. Even if you have a very highly accurate, very fast, low bandwidth systems for the sensing, but it's limited based on these perceptual degraded condition or adverse weather conditions. But the key point is having a stationary sensors that are not suffering from the errors in the visual odometries, errors in the LiDAR slam. And then the V2X is a necessary tool for that. I predict that at least in Canada, we have an open policy for the V2X, but definitely for the short range. It wouldn't be a long range communication. And there are lots of activities here regarding the 5G and how to provide the safe 5G communication between the major suppliers in the communication here, Bell, Rogers, with the vehicles. It's an ongoing project, but I know for the next 3 or 4 years, we're gonna see a huge interest in going back into the V2X, even with the short range communication.
Thanks. We have some earlier stage graduate students and maybe masters and undergrad too in the room. Do you think that cybersecurity of connected vehicle environments is a good area to go into? And I don't know if you have a quick thought or two of important questions, perhaps related to what you just said, that you recommend they could think about.
I think definitely it's worth it, because the major threat that it opens up when we do not have a safe or resilient control systems, resilient to the cyber threats or mitigating the cyber attacks, the consequence would be very huge. And I think when we have an open V2X policy, we definitely need to have a resilient control system into that. And it opens up many interesting subjects. It has been addressed in the literature and the research community for the last 10, 15 years. But it would be huge interest again to mitigate the effect of these attacks.
Okay, I think we're at time. I want to respect you being able to go to your course and your students be able to enjoy you.
Thanks so much
for coming and spending time with us.
Thanks so much, Scott, and thanks everyone. Thanks for having me, and I hope you have a great day. Sorry, I need to drive to another campus for my class.
All right. Take care. Drive safe. Not too much road slippage.
Thank you. Yes. Have a great day.
Thanks, everybody.
Bye.